Hello, good morning, everyone. It's a pleasure to have you all here for our webinar, Technologies Paving the Way to the Circular Bioeconomy. This webinar is organized by Zemgala Regional Energy Agency from Latvia and Biogas Oslofjord from Norway within the Baltic Sea Region Program project BREC, bridging the gap between research and education for the circular bioeconomy. And currently I see we are almost 50 participants already here. My name is Gundars Reders and I'll be serving as your moderator. Joining me today as a co-host is Inga Kreitzmane. Hello, Inga. Special greetings also go to Amalie Lundervold and Selma Solihagen from Norway. They have played, all three actually, an important role in putting together this evening event. Greetings to them. And how are you? You feeling good today? Is it okay?
Good, good. Excited to start and hear a lot of new things.
Okay. Amalie, you're going to introduce us with some interactive survey at the end of this day, right?
Yes, I will run an interactive Mentimeter survey in the end of today.
Yeah, nice. Very good. Short words about this project. So we tackle in this project the challenge of going from linear agriculture economy to circular bioeconomy, and the challenge of teaching and spreading circular agriculture practices that have considerably less environmental impact than conventional agriculture. And during today's webinar and the upcoming Fridays, I'm sure you can expect to discover fascinating examples of circular bioeconomy that will captivate your interest. And we'll have 4 presentations talking about the agenda. Today we have 4 presentations, each approximately 20 minutes long. After each presentation, there will be 10 minutes time for your questions. And we encourage you to write your questions in the chat room. I think it would be most efficient way to get all the questions answered. But of course, you can use mic and speaker after each presentations. Me and Inga will try to collect these questions and get all the questions answered. Let's see how it works. This webinar will be recorded as well, so you can use and share it afterwards. All the information will be with you. So your questions, comments, remarks are welcome in the chat room. You're welcome. I hope for exciting day. And our agenda kicks off with Henrik Bering Christiansen. He will enlighten us on the briquettes from straw. Henrik, let's say stage is yours. You're welcome, and let's start with your presentation.
Thank you very much. I don't know, am I on the main screen now for the moment?
You are on the main screen.
Now I am. Okay, great. Yeah. Okay, thank you.
Good to see you.
Thank you very much, and thanks for the presentation. My name is Henrik Christiansen. As just said, I'm from Denmark, and I work in the company Kinetic Biofuel. I'm going to do a presentation about straw briquettes for biogas production. I'll share my presentation with all of you. What I'm going to speak about is straw briquettes. We have the technology how to use briquettes or to use straw in biogas. Straw is normally hydrophobic, but we have the means of altering this. What will I speak about? I'll speak about how come that you should use briquettes in the biogas plants. What equipment would then be needed if you went down this road of using straw? What are the costs involved in using straw and doing this? And then advantages, and then just in the end, who we are. First one is why should you use straw? In Denmark, we have less than 200 biogas plants. 1/3 of them are very big in size, and they supply gas into the grid. Today, it's getting problematic even finding raw materials. The law is as using energy crops, only 6% is allowed. So that means maize, maximum 6% could be used. So you need to search for other possibilities. And straw, what we say is a second generation raw material, is obvious one to use instead of first generation like maize that you could give to your cow or to the animals or use for feedstuff. If I go into a map of Europe and look for where would the straw be available, then you have the dark brown places. That's where straw is in abundance. If you look here at UK, the eastern side, a large amount of straw available. If you take even Denmark, a fair good amount, and down in Europe, you have areas up here around where you see there are. I haven't focused on specific on this region. This is just one I have for Europe. Similar for Germany, you see dark orange ones are places where there are abundance of straw and availability of straw. Here we have the first generation raw material, and here we have straw in this picture already done as briquettes. And what we say, no, this is in reality wrong to grow maize and other crops in order to do gas. This you should use for a different purpose. You should use the straw. Straw is not grown for this purpose. It's grown for the grains. And then you have the straw as a leftover that could be used. What I have here on the left picture is a picture of the straw. As mentioned earlier, straw is hydrophobic. That means it doesn't take water, it doesn't absorb water. Water runs off from straw. And the reason for this is that you have all of these holes, pores that are filled with air. So if you try to put it into the biogas plant as it is, it will float on the top. When you done the briquetting of the straw, you destroyed all of these pores and holes. And on the right picture here, you see when the straw has been collapsed in the briquette press. And what you saw now, I'll try to take a little back. What you see now is when water approaches, it suddenly blows up and it absorbs the water right away. So by doing the briquetting process, you go from hydrophobic, not taking water, to hydrophilic, absorbing water. When I go for the next one here, then I have a small video showing a unit of briquette presses. It's below in a silo. Here you see the raw material coming down. It's being divided to two sides, falls down, being pushed in front of a piston moving force and back here in the machine, making one long string of briquettes leaving the briquette press. In this case, you see it's running out on a cooling line, and in this case, it's being put into containers. But if you had it in the biogas plant, you could have it close to the reactor. You could even feed it directly into the reactor right away. Very often our clients would have them fall on the floor and have a wheel loader to take them to the reactor and feeding it to the reactor. Here I have a drawing of the briquette press. Here you have the center of the briquette press. It's a mechanical briquette press. It has an eccentric. An eccentric is similar to a crankshaft. When this one moves around, it pushes a piston force and back. You have the piston here. And then in front of the piston, you do the briquette one long string. Strokes of this piston is 270 strokes per minute. So when the machine operates, it goes boom, 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 boom all the time. And by each stroke of the piston, you ruin or you break up the structure of the straw. Here we take in a briquette, put the briquette to water, And here at the same time, we took straw that was not briquetted and we put to water. What happens after 5, 10, 15 minutes? Then the briquette is all absorbed in the liquid, whereas the straw is still on top of it. So here you see that it went from hydrophobic to hydrophilic. A lot of tests has been done during the years with briquettes at university level. Here I just took a sample where it's cattle manure together with briquetted straw, and you have this output. The outputs and these figures you could find at our homepage kinetic.com, and there are a lot of these university reports that has been done in the past. When I have these figures down here, I have the different types of biogas plants, the standard mesophilic and thermophilic, and then different types of biogas plants. Each type of biogas plants would have different amounts of methane being produced. So like the thermophilic here, we say it's 300 on this, but again, these values you could find in the report. But as written here down below, the gas yield will definitely depend on what type of biogas plants that you have and how it is running. At Aarhus University in Denmark, they have a research center, and at this we had a machine standing for like 4 years. When you see this left picture, there is a straw line here behind my cursor. Behind this straw line, which you have here, the straw comes in, it's getting taken apart in a hammer mill. It goes to our silo, from the silo to the briquette press, and then you have the cooling line running away here. The cooling line was in most of the years run behind the feed box here, and then it came up to here, were taken above here on a conveyor, and then at top of the reactor, it was screwed down into the reactor right away. So no storing, but usage right away. What equipment do you then need to make briquettes? I have a line here showing what it typically would look like. Here you have a bale conveyor. Bales would be of course different from country to country or from farmer to farmer. In Denmark, the most common one nowadays is big bales, big square bales with around 500 kilo. In other countries, it's round bales and whatever, but in this case, it's shown with big bales. These big bales is put on a conveyor. On this drawing, there's like 5 bales, and each 500 kilo, 2.5 ton. This briquette press shown in the other end, that's a 1.5 ton. So that means if you had like this, you had more than 1.5 hours production just on the bale conveyor. And there's even empty space. So maybe you could put straw enough for two hours production, and then you need to go back and put further straw. The straw bales are kept together with strings. So either the person that put the bales will need to remove the string, or you put in an automatic string remover. From here in the shredder, the straw is taken apart, and when it's taken apart, it moves forward. When it moves forward, most cases a stone trap is needed. Quite often, bales of straw would contain stone, and if you don't get this away, you could end up having a problem in the hammer mill with sparks, and sparks in a dry and dusty environment would most likely create a fire. In case of a fire, we have a system, a spark detection, and if this is detected, then it would be taken away with water. From there, it goes into the mixer. The mixer is in some cases not needed. If you had straw and all of the straw was 15% in moisture, then you wouldn't need the mixer. But if one bale was 20, another bale was 12, and one was 15, then when it gets into the mixer, it's mixing the, let's say, 5 bales around, and then you'll get an average of the 20, 15, and 12, moving forward to the briquette press. And then from the briquette press, you do the briquette, as mentioned earlier. What I have on this picture is exactly the same as before. Here I have the bale conveyor. As you see here, this is the bale conveyor. And then on the next picture here, this is where it's taking apart the shredder. Then we have the hammer mill. We have a cyclone here, and then it goes into the mixer. From the mixer, it's taken to the silo. And in this case, at Sheppey Island in the UK, they have 2 briquette presses. Each of those is like 1.3, 1.5 tons. So this is a line of 2.5 to 3 tons an hour. At Sheppey Island, it's just being taken out, dropped on the floor, and then they'll take a wheel loader, go in and take a load, go and put into the feed box. Here you see a picture from the feed box. Here you see the briquettes, and here you see cow bedding or cow dung at the other end, and then it just go into the reactor and are being used in the reactor right away. What are the costs then of running? Oh, sorry for this. Sorry, this is modern technology. You get the telephone both to the telephone and to the computer. So sorry. What is the cost of running this? We say it's 75 to 100 kilowatt per ton of briquette you manufacture. For doing the briquetting, it's around 70-75 kilowatts per ton. When you have the preparation line, at the same time the hammer mill, the shredder, and this equipment, then it'll get to a total of 100 tons per briquette you manufacture. Then labor, we say it's quarter of a person to 1 person per shift. So in the line I said before, with 1.5 ton, 3 bales an hour, 1 person, if you had the bale conveyor where you could put 6, 8 bales, then maybe he could come in every 2 hours. If you had 10 ton an hour and you didn't have an automatic string remover, then you would need most likely to have 1 person being around all the time. But everything will be depending on how automatic you do it and how good a quality straw you take. If you use very wet straw in between, you could have problems and you need more manpower. So it's a technology for better types of straw. Then what is the cost of running it? Straw is having a rather high ash content, so there is wear on the briquette press. But what we say will depend on quality of the straw, but normally it's 5 to 7 euro per ton of briquettes being manufactured. Then if I go back to Denmark and about the biogas scene in Denmark, all of the black spots here is biogas plants that is upgrading their gas and sending it into the Danish gas grids. There's like 70 biogas plants that are producing biogas for the grid. Last year, more than 40% of the gas used in Denmark came from these biogas plants. So it's a huge business in Denmark, the biogas scene. There are on this, there's 2 companies, but in reality there are 3 companies at the red stars, where they have lines like you see here, 4 briquette presses, each 2.5 ton. What they want to do is that they would like to produce briquettes and supply these briquettes to all these different biogas plants that are there as a feedstock for them to produce gas. This was 2 years ago, or when the crisis in Ukraine, Russia started, the prices exploded on energy. This was very good business because the gas prices had skyrocketed. What happened in Denmark last year was that we had a beautiful June, no rain at all in June months. And then we had in July, September, August, September, extremely wet. So when the straw was to grow, it hardly grew because there were no rain. And when it was to be harvested, there was a lot of rain. So the harvest last year of straw was lousy. That means straw prices went up in Denmark due to a bad harvest. At the same time, energy prices is down again. And that makes it more difficult to sell straw briquettes directly to the biogas plants. So what happens today is that focus is shifted. Now they make arrangements with the biogas companies that they supply the briquettes to the cow farmers, and the cow farmers use it as animal bedding or cow bedding, and then it's being returned to the biogas. If the biogas plant put in the briquette as it is, they get a sum for the gas that they supply to the grid. But if it has been used as bedding first, then they get a higher sum, and then suddenly it's a better business to use it as bedding first, because then you get a higher CO2 surplus for the gas when you supply that. Then what were the advantages? We say it's a second generation raw material, not a first generation. It's the right way to go to use waste in the gas production. Straw briquettes absorbs after the treatment, and they are easily introduced into the reactor. Straw briquettes can double your biogas production. If you take slurry and this stuff, a lot of the gas potential has often gone lost before it gets there, whereas with the straw, all of the gas potential is still in the straw. Straw, after being briquetted, is a logistical advantage. You could produce it and ship it. They are dense and makes easily handling or simple handling on the biogas plants. It's patented. Even today, trials is made at Aarhus University, and these trials are done for the moment being purely on water and straw, nothing else, but purely these two substrates. And then we say plenty of straw is available in most countries. If not a lousy harvest year, then Denmark as well. Then last, who are we? Kinetic Biofuel. Kinetic Biofuel belongs to two companies. 50% belongs to company CF Nielsen, which is a company making briquette presses, and the other 50% belongs to Biofuel Technology. So when it comes to a briquette press for a biogas plant, then you connect to Kinetic Biofuel. I think this was the presentation I had to show you. I'll just show you what it is that we do at CF Nielsen. This is a briquette, a wood briquette that we use during the winter time for heating up our houses. It could be something similar to this, but when it's for biogas, it's like this. It's made of straw. The quality is much lower than a wood briquette, but after the treatment, you can put it into the reactor and it will be absorbed right away in the reactor. Yes, yeah. Please.
No, it's okay. Are you finished? Are you?
No, maybe I just give you a slight update on what's going on for the moment being at my colleague in Kinetic Biofuel, Torben Bonde. He's the owner of Biofuel Technology. He's working on projects. I don't know how I'll go modern and write in by hand. where they'll take water and straw briquettes only, and that's the trial that they are doing. So they run these trials for the moment being. There's a company in Denmark, and you can look them up later. Maybe you already heard about them. Green2X. They have a homepage, so you can go in and have a look. And what they'll do in a year or a couple of years' time, they are examining it for the moment being. They'll take water, and then they'll take 550,000 tons of straw briquettes per year. So in Denmark, we still have the farmer-based biogas plants, but you know, the big players coming in now, they come in industrial scale differently than what was 20 years ago. So huge amounts of straw is being spoken about for the moment being, and hopefully it's going to come. Yes, this was what I had, so hopefully there are some questions. Otherwise, I explained everything well.
No, you explained perfectly. Thank you for sharing your expertise with us, Henrik. Thank you. So we have time for questions. Do you have any questions? You can raise your hand and we'll try to ask them. I have already some, for example, of course, it's a broad question, but how do you see the future use of straw briquettes in Europe? You show the map, but to be realistic.
Yes, to be realistic, it's one of the main raw materials available. Today in Denmark at the biogas scene, the biogas plants has grown extremely big. When I go to a biogas plant, I hear that the next biogas plants, they come in and pick up their manure and their animal bedding. And when a slaughterhouse wants to sell the slaughter waste, you know, they compete on prices. So everything is around raw materials nowadays to find enough raw materials. And in Denmark, we burnt straw 20 years ago. We don't do anymore. And now it's a matter about who pays the most. There's enough use of straw, but there are plenty of countries still around where straw is not being used. And that would be a waste, and it would be stupid not to take the gas potential out of the straw.
Someone is saying, excellent presentation.
Thank you.
The erratic nature of climate these days could disrupt the straw supply chain.
That's fully correct, but you know, in Denmark we don't have hot summers. We have 22, 26, 28 degrees. If we get 2 degrees more, you know, we don't mind too much, or we don't like it, but we don't mind too much. So maybe Denmark will still stay with straw. Maybe some place that wasn't too much straw will be more straw, and places that was in the past straw will be less straw. So I think that there'll be definitely a change, but I think we still need the grain. You shouldn't grow the corn for the straw. You should still grow it for the grain.
Do you recommend a straw briquette machine for each biogas station, or there is a room for cooperation in the market?
Depending on size of the biogas plants. I mean, if you go into extreme figures like this, then you can't do their own briquettes. You would need to put up a briquetting station in Poland, maybe one in UK, maybe another one, and then ship in briquettes to this. But if you were a smaller biogas plant, you know, like a farmer-based biogas plant, and you had your own straw, then I would do the straw at this place. Otherwise, make arrangement with neighbors that you could get straw from them, and when you finish it and you have the reject from the biogas plants, get it back to the field from where the straw came. But if 3 biogas plants, they could share the amount of briquettes you could do, then that would make a better sense than each having their own briquette press.
So, do we have any more questions, remarks, comments? I don't see for the moment. So thank you, Henrik.
Yeah,
It was
maybe a
excellent.
last one.
Yeah,
I
of
mean,
course.
if some questions pop up later, I mean, just write me. I'll gladly try to help you with further information. So you're most welcome.
Sure, we'll try to help to collect all the questions if someone wants to ask.
Thank you.
Thank you, and let's give Henrik a virtual round of applause. Let's try this way, to using the clap emoji or simply typing applause. Let's see
Thank
how
you.
it works for Henrik. And we can move forward to the next presentation. Meanwhile, so our next presentation, biogas production. Jukka Lehtonen from Metener company from Finland. The Metener is established in the 90s, a bioenergy company that provides environmentally responsible solutions for producing renewable energy in the form of biogas or biomethane. Jukka, are you ready? So stage is yours, please.
Okay, thank you. I am telling a little bit about what's our background. We are providing technology for fermentation and biogas utilization. And I'm showing a little bit what are the most interesting and important points from our point of view as a technology supplier. So please change the first slide. And first, couple of words about our history and background. Our history is already around 30 years, goes 30 years back. The founder of our company, Mr. Erkki Kalmari, he was running a dairy farm at that time, milking cows. And his cows has a little bit problems with their health. There was a bacteria, and it was focused that the bacteria is lying on the manure of the cows. And he was starting to look for ways how to get rid of the bacteria. And his background was technical. He was working before starting farming. He was working in tractor factory, designing Valtra tractors. So he was ending up to try fermentation of the manure. He was built his first small wet fermentation plant, and the results to get rid of the bacteria, they were excellent. But he got also interested about other possibilities how to utilize the gas in different forms, not only only the burning boiler. And this was leading to founding this Metener company at 2001, who is providing the solutions also for other customers. And during that time, a lot of, I would say, pioneering work was made in Finland in this field. He was making his first upgrading unit. It was the first upgrading unit in farm biogas plant in Finland. After that, he was starting to look how to use this upgraded biogas or biomethane. And at that time, early 2000, it was still forbidden to use biogas or natural gas vehicles in public traffic. So it was a long fight to get it legal. So we can say that during these 20 years, a lot has been happening, even though it sometimes it feels that we not get to support enough in this business. At the moment, we are still a rather small company. Our turnover was last year a little bit more than 3 million euros. 15 people are working in our company. But we have been providing solutions already for 4 continents. Okay, please, next slide. And this is the value chain, what kind of applications we are providing to this biogas field. We have our own biomass laboratory. We are very open. The projects are starting so that we are testing the biomasses in our laboratory to see what's the real methane production potential, how we can mix different feed materials, and how the feed materials, how they can be applied in fermentation processes. In fermentation, we have 2 basic technologies. We have this traditional wet fermentation technology, what we are providing, but where our focus is today really is this dry batch fermentation. And I will tell a little bit later more about this method. Raw biogas, it can be, of course, it can be burned directly like that for heating applications. In CHP plants, it can produce electricity and heat. But if you want to transport it or use in public field, public traffic, you must upgrade it first and then compress. So we have our own product for both of these applications. We have upgrading products, hydraulic booster for compressing it up to 250 bars. And we are providing also these transport solutions, different kind of containers for transportation as pressurized form, public refueling stations, and also pressure reduction solutions for to use this compressed biomethane for different kind of use in the industry, in heating, for electricity, and so forth. Okay, please, next slide. Thanks. Here we are concentrating most in these two fields, dry patch fermentation plants and developing dry patch fermentation technology and biogas upgrading and all those applications which are needed after that to compress, to transport, and to utilize biomethane. And we can go directly to the next slide. And here, it was very nice to hear Henrik's speech about this straw. It was very interesting, and we have been found out the same situation. We are closing this. Where to find good feed materials to produce biogas? We are closing it a little bit another direction, but anyway, the feed materials, they are more or less the same. We can see this is from study from Professor Jukka Rintala. He has made this already 14 years ago, but we can say that the situation is more or less about the same still. And I think that this same diagram, it can be applied in all Nordic countries, and why not also in Baltic countries. So the biogas feed materials, usually there are different kind of industrial wastes from food industry, other industrial slurries like from forest industry, and then there are this kind of every kind of municipal wastes in slurry form. But we must say that most of those feed materials, they are already in use in the biogas plants, so there is not much potential left. In agriculture and farming, because there are still a little bit slurry manures and dry manures to utilize, but there is no much available. But if you are looking about field biomasses and other dry biomasses, we can see that there's a vast potential. So of course, it's not possible to utilize all of that potential because we need something to feed the cattle. We have to feed the people. But there are a lot of, for instance, straw, and there are areas where are not any more cows to feed. So there is plenty of field biomasses available for biogas production, and that's why we are concentrating in dry patch fermentation where this kind of feed materials can be used. Okay, and now we can step to the next slide. And there's a quite large amount of different biomasses which are suitable for dry patch fermentation. Typically, they are slowly degradable, so it's difficult to utilize in wet fermentation, or they are technically difficult to utilize there. For instance, straw, it's floating and it's very difficult to mix in the reactor. So there is straw, hay, even grass silage if it's allowed, but there are certain limitations to use it for biogas production. There are even some wood-based materials which can produce biogas in dry batch fermentation, and of course dry manures. In shorelines, there is plenty of reed and cane, for instance, and quite often we are trying to clean out our shorelines from this kind of and get the nutrients from the water and transfer it to the fields. And the feed materials what we are using there, they are typically quite dry. Dry matter content is 30–40% or even more. And as always in fermentation process, the nutrients they are remaining in during the process. So the digestate what we are getting out from the reactor, it's valuable fertilizer, or even a little bit better than when it's going inside to the reactor, because some part of the nitrogen is changing into soluble form, so it's more easy to use by the plants. Next slide, please. And this is a simple diagram how dry batch fermentation working. We have the typically silos which are made of concrete. It's possible also to make steel silos, but concrete is more economical and it's the most in use. There is no mixing or stirring or heating inside the reactor. We are packing the feed material. It should not be densely packed, and we are leading their so-called percolation fluid, which is containing the archaic bacteria which are producing the methane. We are pumping it on top of the feed material batch. It's flowing through the feed material to the bottom of the reactor, and we are collecting it from there and sending back to the tank. And the tank is kept in mesophilic temperature between 35–40 degrees. Gas is collected both from the reactors on top of the reactor and also from the percolation tank, and it's going to the use, whatever is the utilization for the plant. Typically, it's around 3 months retention time for one batch, so it's roughly 3 times longer than in wet fermentation. So that's because of the feed material nature. It takes longer time to utilize the methane production potential. And typically, we can say that all the machinery what we need in this kind of plant and production, it's quite simple, it's robust, and it's cheap. So the investment what you need here is, if you're calculating on per kilowatt hour, it's quite reasonable. Next slide, please. Here are some examples. These numbers they are given per wet weight ton. So as this we are talking about biological materials, there is certain variation, but these are quite normal production rates what we can expect from different kind of feed materials. Straw, hay, I think they are the most important, and their availability is the best one. Next slide, please. And here we can see some examples how the feed materials, how they look like before fermentation and what they look like after the fermentation process. So typically, if we are putting in material where it's as an average 35–40% dry material content, it's coming out in 20–25%. It's very easy to spread to the fields with normal manure spreader, so there's no special treatments needed for this digestate. Next slide, please. Here are a couple of examples how these dry batch fermentation plants look like. On the left side, there is a plant which is at the moment just in commissioning. They have been starting to produce biomethane already. There are the first batches in the both reactors, and they are closed ones. So the reactor is inside this kind of steel hall or hangar type of building. So that's quite neat in our environment, and also we are eliminating every kind of fumes what could go to the environment. So this kind of plant is quite easy to build also where is habitation nearby. On the right hand side there are open reactors. So this on the right corner there is the reactor. The size of the reactor is here, width is 12 meters, length is 30 meters, and depth is 3 meters. So it's about 1,000 cubic meters for each. And we can see the next slide, please. And here's a picture from one biogas plant in building phase during the construction. So there is easy to see how the construction is made. So that's quite normal concrete silo. It's of course it's insulated because to minimize the energy loss. Behind the silos there is the technical room. There is gas collection. There is percolate pumping, and there is also heating. And you can see that on the floor of the reactors there are those 3 grooves on both of those. They are for collecting percolation fluid when it has been floating through the batch. It's collected from there and it's sent back to the tower, which is back there, and that's the percolation tank. In this application, all the gas is used for heating. The farmer here is growing turkeys, and the turkey growing needs a lot of warmth, especially in winter time. So all the production from this plant is going to heating this turkey production facilities. Okay, and next slide, please. And here are the references so far. We can say that all of these references, except the second from the top, are for agricultural applications. This Kymenlaakso-Jäte, it's a municipal waste management company, and they are using mainly every kind of waste from the city parks, leaves whatsoever. But most of these others, they are using the field biomasses. The fourth from the top, Hebei province, China. This is interesting. This plant is using only straw, but in this case they are using rice straw. But we can say that straw in every plant it's quite good for feed material for this kind of fermentation. And we can jump to the next. And then a little bit about biogas upgrading. The method what we have been choosing in our upgrading technology is water scrubbing, and that's what I know. It's the oldest way to upgrade biogas. We can say that, especially when we are talking about application in agriculture, this is quite a robust way to upgrade the biogas. Hydrogen sulfide is not a problem. There is no pre-treatment needed for biogas. It perhaps makes so that we have to change the scrubbing water a little bit more often, but there's no other harm from high hydrogen sulfide contents. Here you can see that also that we are providing quite small applications, because this is really something we like to get this also these small applications is in farming economically viable. So I think that 150 cubic meters, they are typically right sizes for instance dairy farms here in Nordic countries. We can step to the next slide, please. And this is simplified process of this water scrubbing process, how we are upgrading the biogas with that. Biogas is coming from the left. It's going to the bottom of the first column here, the big one in the left. It's so-called absorption column. And it's flowing from down to the top of the column. And at the same time, we are pumping water on top of the column. So water is going downwards and gas is going upwards. And the water flow is washing away the carbon dioxide and hydrogen sulfide, and also great part of siloxanes. We are collecting the biomethane from top of the column. It's going to gas drying, and it's odored, and it's going where it's used for quite typically it's going for compressing, and it's compressed for refueling or to the container to be transported to some usage. Water is continuing from the bottom of the absorption column to the small column in the middle, so-called flash. And the residuals from the water, residuals of biomethane are still collected from the water. And that residual is going in the beginning of the process. Water is then continuing to the big column on the right, so-called desorption. There we are releasing the pressure from the water. So it means that all the gases which have been solute into the water, they are released. And the water is going back to the circulation again. Okay, we can go to the next slide, please. Here are some examples of the references where we have been providing our upgrading technology. These first ones here, they are rather small. These 10 cubic meter solutions, they have gone to the university purposes, so they are for research purposes. But the bigger ones, starting from this 40 cubic meter, they are commercial solutions. And as you can see, there are the feed materials where these are applied. There is several big variation of different kind of feeds. We can go to the next slide, please. Here, the three last, okay, this Pyhäjärvi, the third last, it's at the moment also in commissioning. It's starting to operate during this month. And these two last are at just moment, they are in ship in container going to the USA to Minnesota. There are two cow farms where are biogas plants under construction. And during next summer, they are installed besides these biogas plants. They are starting to produce biomethane to the interstate gas line. And this is quite exciting to see that this process towards the green energy, it's going also forward in USA. Okay, we can go to the next slide. Yeah, here we have some examples of how to utilize biomethane. Okay, of course, on the right-hand side, there is refueling stations. it seems unfortunate that personal vehicles, the number of those which are running in gas, it's going down. But in heavy traffic, I think there is the hope for this use of biomethane in traffic. Biomethane can be used, of course, for heating, producing eventually even electricity. And there are also quite big variation of industrial use where it can be utilized. We have been delivering solutions to use biomethane, for instance, for carpeting shop, wood panel decorating, steel component deburring, catalysator testing. So it seems that only the imagination can be the limit where you can apply this material. At the moment, we came to the last slide of this presentation. So thank you for this opportunity to show what we are doing in this biogas field. And now I'm ready for some questions if there are some questions coming.
Yeah, Jukka, thank you very much. Thank you for the presentation and where you shared actually your company's 30 years of experience, and which a round of applause goes to Jukka. And we have a couple of minutes until we move on the next agenda item. And we have one question and one comment. Narasinya Shurpali. I'm a principal scientist at Luukamaninka. Our biogas plant has been set up by Metener in 2010 or so. Metener, as an industrial partner, has provided in-kind research support to my Academy of Finland project. A big thank you.
You're welcome.
Yes,
that's nice to hear.
Of course, and there's a question as well from Narasinya. Reed canary grass was a popular bioenergy crop in early 2000. However, WAPO had problems with it for combustion. Nowadays, paludiculture is being recommended for drained peat soils. How do you see the future of reed canary grass production in this new scenario? We have 20 or so original research papers showing how environmentally friendly is the reed canary grass.
Yes, that's interesting. I think that one problem has been that the business has been quite limited before this unfortunate Ukrainian crisis. And we have to say that all the demand for biogas and request for quotation, it was exploding after this Ukrainian crisis. And I think that we are going towards that we have to put all the horses in the race. And I think it's question of time until we can utilize, for instance, all of these. I know we have been making tests. I think there are something like 150 different kind of feed materials tested in our laboratory. So there is a vast potential waiting for utilization.
Jukka, thank you very much. Thank you for your expertise. And again, applause goes to you. And again, I want to remind that you can have your questions and we can collect them and deliver to speakers afterwards. And now, without further ado, let's move on to our next speaker, Anna Lundbom, Easy Mining Sweden. Easy Mining is an innovation company focusing on closing nutrient cycles. So Anna will introduce us to the company's technologies for phosphorus, nitrogen, and potassium recycling from different waste streams in society. Anna, the stage is yours.
Thank you very much, Anders. Hello, everyone. Nice to meet you. I'll just share my screen with you here. No. Now, did you see my screen?
Yes. Yes.
Good. Very good. All right. Yes, as Anders said, my name is Anna Lundbom and I'm the marketing manager at Easy Mining. And I'll be telling you a little bit about our technologies for closing nutrient cycles. I know it stood only phosphorus recycling in the agenda, but it's for 3 different nutrients that we I will be talking about. But first, very short about Easy Mining. We're an innovation company within the REC Cells group. We are now plus 45 people and are heading towards or forecasted to be plus 50 people plus in the end of this year. So we're growing very rapidly. We were founded 2007 by our head of engineering, head of research and development, Jerry Cohen. And we're mainly based in Sweden, but we also are based in Germany since a few years ago. And as I said, we're fully owned by the REC Cells group, which is one of the largest waste handling companies in the Nordics. And in Easy Mining, we're focused on chemical process, and we have 3 different processes that we work mostly with. And it's Aqua to N, where we remove and recover nitrogen from liquid waste streams, for example, from react water, from wastewater treatment plants. But we've also been, if you to refer back to the previous speaker, we've also been looking at digestate from, or the concentrate really from dewatering, the digestate from biogas, from manure, for example. Then we have ash to phos, where we extract and recycle phosphorus and other resources from incinerated sewage sludge. And thirdly, we have ash to salt, where we recover pure salts from fly ash from incinerated municipal solid waste. The status of these different technologies is that we're in the start of the rollout phase for all technologies. And the Aqua to N process is demonstrated in operational environment, and here we now are conducting the first feasibility studies for full-scale implementation. For ash to phos, we're just in the beginning of the detail engineering phase for the first plant in Germany, in Schkopau, that we will own together with Gelsenwasser. It's one of the biggest water utility companies in Germany. And we're also doing the basic engineering for a plant in Helsingborg in Sweden. And then for the ash to salt, the first plant was actually inaugurated last year in Stockholm. Also Stockholm in Sweden. But to start off with, we'll start with the ash to phos, since that was the one that we were talking about first. And as I said, here we work with incinerated sewage sludge as a feedstock, and we recycle clean phosphorus products. As I'm sure that most of you know, phosphorus is a finite resource. And most of the phosphorus that is left in the reserves today are in Morocco. Also, the phosphorus that we have left in this soil or in the ground, most of it is actually also contaminated with, for example, cadmium. It has quite high levels of cadmium in it, which is not good for neither us or the animals we use it for feed. So given this, in a few years, or in our lifetime, the world will be mostly dependent on Morocco and China for the phosphorus supply, if we don't actually use the phosphorus that we already have in our sewers. I mean, the sewers that we have is a fantastic source of both phosphorus and nitrogen, but now we're focusing on the phosphorus here. What we want to do with the ash to phos technology is actually closing the loop. So the phosphorus that we have in our sewers, we want to recover that and recycle it in a form that we can use it again in, for example, producing mineral fertilizer or using it directly in agriculture again. We might not be able to take away all the mining of phosphorus, but we will certainly supply a significant part. The plant that we are planning in Helsingborg, Sweden, would, for example, supply 20 to 25% of the phosphorus that Sweden needs for mineral fertilizers every year. So we should really take care of the phosphorus that we have in our sewers. The ash-to-phos technology, in this technology we use not only the ash, we also wash the ash with hydrochloric acid, and we also use some lime in the process. In the process we extract or take out the heavy metal concentrate to ensure that we detoxify the products, because that is a very important part for us. So we should not send back anything that is unwanted to the society again. In the process, we produce then a clean calcium phosphate that we can use in either directly in agriculture or as a raw material in mineral fertilizer production. But we also get out the ferric chloride that can be used as coagulants in wastewater treatment plants, for example. So we could close that loop as well. And we also get out an aluminium chemical, either an sodium aluminate or aluminum hydroxide. And then we also get what is left is a sand that can be used in construction materials. We have done a project together with the Danish Technical University, showing that up to 20% of cement in concrete can be replaced with this one, with this sand. So, excuse me. The products, as I said, with the ash-to-phos technology, we actually utilize more than 95% of the ash, and we get out clean, well-known products. And you see here the pictures of the products that we talked about. You have the ferric chloride, you have the calcium phosphate, and the sodium aluminate, and then the sand. The sand is red due to this the iron that is left in it. The phosphorus, the phosphorus, as you see, is very pure. It's actually, we have taken away more than 96% of the heavy metals that's in the ash. The phosphorus is purer than most of the phosphorus that's actually mined today. It's comparable to the coal apatite, or the phosphorus on the Kola Peninsula. Given this, it can be used either, as I said, as raw material in mineral fertilizers, or directly as a slow or controlled release fertilizer. And it can also be used as a feed phosphate. We have done trials there with pigs and chickens with very good results. So the quality is good, the digestibility is good. However, the European legislation hinders this application due to the origin, not the quality. Here we are now looking into the Canadian market for the feed phosphate, given that it's so well suited as a feed phosphate. To sum up the ash-to-phos technology, with the ash-to-phos technology, we reduce the dependency for importing phosphorus, so we have a domestic production of phosphorus, really. We utilize more than 95% of the ash and recover over 90% of the phosphorus that is in the sewers. And then also, in addition, we recover other important resources as well. The output products, or the quality of the products, the phosphorus product, the iron product, and the aluminium product is independent of the ash quality going in. This is also very important, so you have a robust technology. And we separate out the heavy metal concentrate. Also, the process is aligned with the European strategic goals, and also the future legislation that's coming up now with recovery rates and quality. Going to our next technology, the Aqua2N technology. This is where we remove and recycle ammonium nitrogen from liquid waste streams. And we're focusing on liquid waste streams with a high concentration of ammonium nitrogen. So for example, this is from a wastewater treatment plant. The stream that is interesting for the aqua-to-end process is the sludge liquor, or the REC water from the dewatering of the digested sludge. So the mainstream is the nitrogen concentration is too low to be of interest there really. So it's liquid waste streams with a high concentration of ammonium nitrogen. Sludge liquor is mostly about between 1,000 to 1,700 milligrams ammonium nitrogen per liter. If you have a thermal hydrolysis process first, you can be almost up to 2,500, maybe 3,000. That also works well. We're also looking at other waters or centrates at the moment that has a even higher concentration than that as well. That is very interesting. On these waste streams today, if you have some treatment, you most of the time have a biological process that removes the nitrogen, not recover it. And also, for example, if you have the NMOX, you have a risk of releasing a lot of nitrogen as nitrous oxide. What we see now is that there is new legislation coming up, which has both a stricter limit for nitrogen into effluent. You also have requirements of recovering nitrogen and also start measuring the nitrous oxide emissions if you look for the wastewater treatment plants. And this is also important things of taking into account when looking into how to remove and recover your nitrogen. The aqua-to-end process as such, as I said, it's applicable on liquid waste streams with a high concentration of ammonium nitrogen, and we can lower or we can remove nitrogen down to about 40 to 50 milligram ammonium nitrogen per liter in the treated water, almost independent on the incoming concentration there. It's a chemical process in 2 steps. So first we have the catchment step, where we catch the ammonium nitrogen with a precipitant. The precipitant that we use is a magnesium phosphate, so we really work with the struvite precipitation here. The struvite is then going into the next step, the conversion step, where we add an acid. And so far we have mostly been working with sulfuric acid. With acid, we split up the struvite, we regenerate the precipitant, which is sent back to the first step again. So we have a loop where we're circulating the precipitant. And we form the ammonium salt. Working with sulfuric acid, we get an ammonium sulfate. We can also work with other acids and get other ammonium salts if that's wanted. And one important aspect here is that this process has no nitrous oxide emissions. Working with sulfuric acid, the ammonium sulfate that is produced, and this is what we have used or we have produced in our demonstration plant for the process. It's a liquid ammonium sulfate, as you see on the picture here, of about 40% solution. You can also go to a dry one. But then you need to add a drying step. So in the process, we stop at 40%, or 30 to 40%, depending on how close to 40 you want to go. Important is that the process or the product, when it comes from wastewater treatment plants, fulfills the end of waste criteria and the European fertilizer product regulation. If it's of other origin, the water concern will have to look at if the origin is approved in the EU fertilizer product regulation. The products as such can be used on its own or mixed or blended with other fertilizers or slurries. We have done agronomic agronomic tests like with pot trials to prove the agronomic effect, which is comparable to or the same as conventional ammonium sulfate. And we've also done an LCA to look at the climate impact or carbon footprint, which is significantly lower than conventional produced ammonium sulfate, even before you take into account the reduction of nitrous oxide emissions from, for example, wastewater treatment plants. To sum up this technology, as I said, we remove and recover more than 95% of the ammonium nitrogen. It's a robust process, and it fulfills the regulations that exist. We have a lower carbon footprint, both for the process and for the product. And it will also help the operators, if you look at wastewater treatment plants, to fulfill upcoming legislation. And finally, then the ash to salt technology, where we work with fly ash from incinerated municipal solid waste as feedstock. The fly ash from these incinerations is a hazardous waste due to the very high levels of salt in it. It have an average 20%, but can be up to 40% chlorides in the ash. And also they have also the heavy metals, of course, is also one of the reasons for the hazardous waste. Interesting with this one is that the salt content is above the limit for the landfilling of on hazardous waste landfill. So this is a very complicated material to handle, or waste to handle. In Sweden, we produce about 300,000 tons of fly ash annually. And this is why we came up then with this process, since Briquettes is a large player on this field, and they wanted to have a more sustainable way of producing or treating the fly ash. And also in the fly ash, there is the resources that is interesting and important to take care of. So what we do is that we take in the fly ash, we wash it with water. From the salt brine that we get out from the process, we separate potassium chloride, calcium chloride, and sodium chloride. And this can be used in different applications within the society. So this is the really important feature of this process, is that we separate these three salts, and we don't have a mixed brine that just if you only wash it with water, you will have a mixed brine. In addition to the salts, we also get out heavy metal concentrate also from this process. We get an ammonium sulfate, and we get the residue ash, or that we're also looking into how we can use that in the society. The plant that is now built outside Stockholm in Sweden, it is owned by our sister company, Briquettes Treatment and Detox. It has a capacity of 135,000 tons fly ash per year, so almost half of the annual production in Sweden. And what we produce there is, in this plant, about 3,500 tons dry potassium chloride, 7,000 tons dry sodium chloride, and then 32,000 tons liquid calcium chloride. And what it can be used for differs from salt to salt. Important to mention is also here is the purity of salts that is very important. As I said, we don't want to spread something hazardous into society again. On the picture here, you see the fly ash that comes in versus the recycled sodium chloride. To mention again the purity, the potassium chloride that we recover has a more than 99.1% purity. In the Nordics, we work with the GC Rieber. It's a salt company, Nordic or Norwegian salt company, that is offsetting the salts. And important here as well is the carbon footprint of the salts, which is much better than the conventional salts. That was all that I had. Thank you for listening. Do we have any questions?
Thank you, and it's a great job on the presentation. And yes, we have a question. Thank you for the presentation. And the technology is very interesting. Can you talk a bit about energy consumption of the H2 technology?
You mean figures? No, I don't have the figures in my head. Of course, we use energy.
Yes. In general, I know how
what
it is meant, but in yeah, a bit
what
about.
we can say is that the H2 technology, it's a centralized technology, or like a centralized plant. So the Aqua2N, that's a plant, or that the process will be applied on the site where you have the REC water. However, the H2 plant, that is bigger plants. The plants that we're planning now is 30,000 tons ash per year. So you will have several wastewater treatment plants and probably several incineration plants feeding into one plant. So it will be energy. You can place a little bit where the feedstock is. For example, the acid, and the energy is available. But I don't have figures in my head of exactly how much we use per ton there.
Yes, and you talked about this replacing imported phosphorus. Do you have any targets in the future? Is it possible for Sweden, for instance, to completely replace imported phosphorus?
Not by only circulating the phosphorus that is in the sewers and not doing anything of the usage of fertilizers. That would not be possible. You would be able to replace about 50% maybe in Sweden, but at the same time, I think
How many percent?
50% if you would use everything. I think if you would incinerate it, all sewage sludge, and recover it with H2 technology, I think you would be about 50%, maybe a little bit higher in Sweden. At the same time, I mean, there is, if the sludge is of good quality, you can spread it directly there as well. You can discuss how well the plants take it up, but that's possible. But important here as well, I mean, there is a very interesting and important work going on from the fertilizer side as well, working with how you use fertilizer, and what kind of fertilizer and how you use it. So I think we will, I hope that we will be more specific in our use of fertilizers, which will bring down the need of the amount of phosphorus needed. And then we can replace an even larger share.
Cool. That's great. And I have one more question here. How do you see the future of technologies offered by easy mining in the context of moving towards wider use of circular technologies?
We are experiencing a great interest for our technologies, and it's increasing. The interest is increasing every day, I would say. I've been working at Easy Mining now for 2.5 years, and I see a big change in the interest. So I mean, we really believe in our technologies, and we really believe in circulating nutrients and other resources as well. So I think we this industry, or what you would say, I think we will only see an increasing interest and demand for circular solutions. Absolutely. And I mean, there is also legislation pushing for that with the Circular Economy Act. And if you look at the EU Circular Economy Act, it's going For example, the wastewater treatment directive now is including recovering of phosphorus and nitrogen, and so we're seeing both an interest from the market and a push from legislation.
Anna, thanks again for your insightful presentation. Thanks for your answers, and good luck.
Thank you very much.
Thank you very much. And we are moving forward. Our next speaker, Richard Lokstrup. Hi.
Hello, can you hear me?
Hello. Yes, we hear you. And Richard has been working for GEA Westphalia separator for 15 years. Having a technical background, he believes that the main thing is in the knowledge, how to use the technology and what it can be used for. Richard, stage is yours.
You see my screen?
Yes, manure and digestate.
Perfectly. And I will just go to like that. Good. Yes, as you said, my name is Richard. I come from GEA Westphalia, and I've been working 15 years with this application and also 15 years with the company. When I joined Westphalia is a really old company dating back to the 1800s. When I joined the company, I was told that the first 10 years you are here, you are a newcomer, and then you advance to trainee. And after 20 years, you start adding value to the company. And I said, yeah, come on, guys. But every day that goes by, I'm closer to that truth, actually. Yes. No, I'm going to talk about manure and digestate separation, which is kind of two sides of the same story, especially in terms of technology and machines used for solving that task. We're talking about manure separation, which happens on the farm, and then we talk about digestate separation after the biogas plants. And we're going to deep into why it makes sense and how you do it. And I would also kind of take away my GEA hat and talk about other technologies which can be used. And when we come to discussing about digestate separation, then there are a combination of different technologies. We in Westphalia, in GEA Westphalia, only handle decanters and not other technologies. So we are but we are cooperating with other suppliers in order to supply systems, basically, when we talk digestate. So manure and production of livestock means that you have an excess of nutrients from the production of livestock. And there are three main categories. There's cows, there's pigs, and there's chickens, basically. So and it's fairly easy to put them into categories and define what you can do on separation of nutrients with these three products, basically. The chicken manure is normally is not something which it's being digested, not being processed through separation, because it's a dry product. But when you feed that into a biogas plant, it's very heavily on the nitrogen. So it becomes into a focus area when we talk digestate. Basically, when you have a farm, you produce a certain amount of animals, and then produce a certain amount of nutrients. The legislation in the EU is setting a certain limit on the amount of nutrients that you can spread on the land, which means that there is an upper limit for nitrogen, there's an upper limit for phosphorus on the land. And this means that when you produce a certain amount of animals, you produce a certain amount of nutrients. So you need to have the land available that corresponds to that production, basically. If you don't have that land available, you have two options. You can take the manure and drive it away, maybe get rid of it for another biogas plant in the nearby county or whatever, or you can do a separation of the nutrients, and you can separate the manure into two fractions, a solid fraction and a liquid fraction, basically. So those are the two options for the farmer if he wants to produce more livestock than he has available of land. I think it's obvious why it makes sense to control the nutrients that is spread on the land, and it's of course to handle the excess of nutrients. So if we just spread more nutrients than the land can absorb, or the crops that we grow on the land can absorb, then the nitrogen and the phosphorus will go into our water system and will pollute our water system. And eventually what will happen is that the lakes, the sea and so on will die, and the fish will die, and we really don't want that, basically. So we have to control how much nutrients and fertilizer we put on the land, basically. As I said before, when we talk about new manure treatment, then the manure can be split into two phases. The centrate, which can be handled with these things that I describe here. I think in 99% of the cases, the centrate is used directly as a fertilizer on the field, and the solids, or the cake, depending on what you want to call it, is also being, well, there's a lot of things that can be done with it, but normally in Denmark you use it for in the western part of Denmark. There's a lot of sand inside the land and so on, so it can be put on the land and used as a ground improver, basically. It's also very good for when you want to grow Christmas trees, actually. So as a starter fertilizer for growing Christmas trees is very good. So a lot of that is going for that as well. A new thing that is popping up these days is pyrolysis of the solids, and which will actually convert the carbon inside the cake to energy, which can be used for cleaning the biogas upgrade, and also for heating and other things on the biogas plant, basically. Pyrolysis is one of these things, and also you do I'm not an expert on pyrolysis, but what I hear is that you can also do CO2 capture with that technology from that cake. From the Danish government, it's something which is on the radar as one of the solutions for Danish agricultural industry in order to actually be sustainable and actually have a future. So yeah, this is typical results that we see. I won't go into details with that, basically, but this is I guess you will have the presentation afterwards, so you can have a look at that. But this is how a typical pig manure and cattle manure and chicken manure looks like. And there is actually regionally differences. So there's I don't know why, but the composition of pig manure is very different from, let's say, Holland to Denmark, and I think maybe it's according to the traditions you have on feeding the pigs and so on. Cattle is a little bit more similar across Europe, but there's a relatively large difference on the pig manure. Yeah. So when you have a farm and you want to do separation, so basically the first question when I get a call from a farmer wanting to look into separation and nutrient management and so on is that, how big is your need of controlling? How much nutrients do you need to remove from your nutrients balance accountanship? And if you say that I just need to remove some of it, then I would advise him to go for the screw press technology. If he's looking into maximum phosphorus removal, there is a thing that the phosphorus removal, which is on the radar, is that the phosphorus is connected to the particles inside the manure. So the better your separation efficiency is on particles, the better phosphor capture rate you will get. So if you only need to remove some of the nutrients, then go for the cheaper solution, which is the screw press or other technologies, but mostly common used is the screw press. If you really need to push it to the limit, you have to go for a decanter. The decanter is a much more expensive technology, especially on the OPEX side, but I will come back to that. But the first question is, how much do you need to remove? There is also discussion whether or not to use polymers or ferro or other precipitants in front of the. It's not that that the machine will not work without it. Basically, it's something you can add on, and if you really need to increase the capture efficiency and remove all of the nutrients, basically, which is possible by mechanical separation, then you need a lot of polymers and so on. We saw that in the beginning. When I say beginning, then we are talking 20 years ago, something like that, where this manure separation came up in Europe. So basically, but today, none of the farmers in Denmark are basically doing separation, and none of them are using polymers. It's a very huge expense. And on top of the expense for using the polymers, you have the water consumption. So if you need maybe 5-10 cubic meters an hour of water that needs to be transported to the land afterwards, and which is not really feasible. And then we have the whole discussion about, well, polymers is basically liquid plastic that we put into our manure, which we then put on the field afterwards. There is a tendency or a movement in looking into different kinds of technologies instead of polymers. We don't really have a good alternative at the moment than these mechanical produced polymers and so on. So yeah, it's a fairly simple, robust process using, if you design the system correctly. There is a lot of things that can actually go wrong. Manure is a very difficult product to handle, but if you get it right, if you use the right equipment and you design the piping system and your scroll conveyors, etc., correctly, then it's actually a pretty simple system and simple application in our mind. So this is the typical results that we see with decanters. I put in with polymers, even though that it doesn't make sense, but just to give you an idea what we see of separation efficiency in terms of nutrient, both N and P, and a little bit focus on K, but it's not K which is the most important thing here. It's the phosphorus is most interesting to look at. Yeah. I want to put some words on this one, because this is something which I experienced is a little bit difficult for people to realize. Actually, when you have a manure, there is a tendency that you talk total dry matter. But when you talk total dry matter, there is actually suspended solids or salts, and there's suspended solids in there, but there's also insoluble or soluble salts and solids. So when I have an example here of 8% DS, up till half of that total DS could actually be soluble salts and solids actually. And no matter the no matter the technology you use for separation, the solubles, solids and salt will actually go directly through the machinery which is used. And the separation technology can only handle the suspended solids actually. And this is something which also today is a little bit difficult, especially when we talk the biogas people, because the biogas contracting people and so on have they only look at total solids basically, which is kind of a problem actually. There is a thumb of rule here. I could have written it in, but a thumb of rule is that when you have a manure or a digestate which is based on manure, then 1/3 is soluble and 2/3 is suspendable solids actually. Yeah. The product that comes out of the separation, I have shown mobile units here. We have a vast fleet of mobile units, both customers and internally and so on. The solids that comes out look like fibers and so on. The fibers, which is normally that comes from manure, is around 30%, maybe a little bit lower to 28 and so on. There's the DS out of the screw press is higher due to the water follows the small particles, and the separation efficiency for the decanters are better, which means that more smaller particles are captured by the decanter, and even more when you introduce polymers to the feed for the decanter. So the more finer particles you will capture, the wetter the cake will come out of the separation equipment. Screw presses, there's a vast variety out there of suppliers and different designs of screw presses. I have shown 2 here, which is quite common. I have shown the Burger screw press from Germany, and there's a fan screw press as well. I see the fan screw press is a smaller screw press, farm-based basically, which is I think most of them handles 1, 2, 3, 4 cubic meters an hour, maybe more if the manure is a little bit thinner. Really simple, easy to operate machines and so on. The Burger screw presses can be used for industrial uses, and we are talking about large scale screw presses here. We're talking up to 150 cubic meters an hour of solids or in feed they can handle. But there's a huge amount of different suppliers out there, and it's a fairly simple machine. As always, when you talk a simple machine, the devil is in the detail basically. So there's a big difference on design of these machines, but there's a vast variety of suppliers out there. So the pros and cons regarding the screw press: it's fairly easy. It's a simple machine. It's relatively cheap. You get high DS of cake. If you are looking for maximum separation efficiency, then this is not the right way to go. You separate mostly the large fibers, and thereby you also have a lower separation efficiency. To put some numbers on the separation efficiency, what typically will happen if you have a one-stage separation with a screw press is that a 250 micron screen is installed in that screw press. So basically the solids that is above that screen size will be captured by the screw press. And if you go to a decanter, then actually what we see is that the cut is around 30 to 40 microns. So basically we capture the difference between 200 and 250 microns and down to the 35 micron mark is captured extra with the decanter, which makes a difference in separation efficiency. 20 years ago, 15 years ago, when this was a big thing in Denmark, then we saw Kemia introduced a separation efficiency separation system, which was based on a belt press, and actually they utilized the screw press in the end of the belt press. The system uses precipitants and polymers and so on, and was really high in capture rate, but it was sold as a farm-based thing, and I think when the golden days were there, they had 35, 40 systems running in Denmark on farms and so on, but there's none of them actually working today, and so there's been a big shift in the industry that all the manure basically today goes to, not all the manure, but most of the manure today goes to biogas plants. So the nutrients handling is done within the biogas plant. It's a cheap solution, very, very good separation efficiency. If I had to, with the decanter, to match the separation efficiency, I had to add polymers to the decanter in order to match the separation efficiency which you can get out of the belt press. There's a lot of disadvantages with the belt press, and also why they are not running today actually. But the main thing is that it's an open system. Basically, it really smells a lot, and when you separate manure, the nitrogen in the air is really, really bad, and the air inside these containers and separation systems are extremely bad, and are not nice to work with. And then to sum it up, I end with the decanter. When we talk biogas plants, then the preferred technology is decanters, and the main thing here is actually that you get the best cubic meters per square meters. Basically, the throughput you need on the large scale biogas plants, when we talk 800, 900, even 1 million tons of in-feed per year, which is quite common these days actually, then there's a lot of manure that needs to, or digestate, which needs to be handled here, and then the decanter is the preferred machines. Yeah, and again, disadvantages: we are really expensive. We are the expensive guys to play with, basically, both in terms of the machine equipment. The materials we use to build the machines are duplex steel, and it's very high G-forces that we work with, so safety is a priority and so on. We are the very expensive guys to work with, basically. But if you need to go to maximum separation, you have no other choice than utilize the decanter. Then I'm moving on to the separation of digestate or biogas. There's a lot of drivers in this industry and so on, and I guess that you're all aware that biogas is a growing thing and so on, and especially when we saw that Shell acquired Nature Energy, which is a large scale one, maybe one of the biggest contractors in the world, could be. When you see Shell moving into that industry, then it's also because they see that biogas and is a big thing for the future, and it will also require a lot of nutrients handled. So when we talk biogas plants and so on, there's a big struggle in Denmark actually to get enough feed to feed all these biogas plants. So they are taking. They're not taking not alone nutrients from the farming industry. They're taking nutrients from household wastewater, canteen waste, and so on. All these waste streams they take into the biogas plants will create an excess of nutrients on the backside of the biogas plant. So utilizing the manure in these biogas plants actually increases the problem of nutrients handling, and that's why we see a growing interest in utilizing the separation on the backside of the biogas plant. So if you look at a biogas plant, you also need a balance between the land you have available for spreading your nutrients, quite exactly the same as a farm. So it's the same thing. They have to handle the amount of nutrients, and they have to document where they get rid of the nutrients, and they have to spread it on the land where there's limitations on the land. Until Corona, there was a big problem in Denmark with the nutrients, and especially the phosphorus. There was a big excess of phosphorus in Denmark as a whole, basically. But yeah, we removed the minks from Denmark, and actually removing the minks from Denmark actually removed 25% of the whole phosphorus amount in Denmark. 25% in one overnight, basically. So today we have, if you looked at the whole country, there's a balance between the nutrients we produce in the farming and actually what we have of land available actually. Yeah. So I won't go into that and read it and so on. You can read it afterwards, basically. So the application is maybe 25 years old, something like that, where it came up, and that time we all went for one stage, and we had a lot discussing about screw presses versus decanter versus belt presses and so on. And it's still one stage if you talk about manure and some biogas plants. It's relevant to talk about one stage and so on. We still sell machines all over the world. We sell around 100 machines a year for this application when you say manure and digestate. So there's a lot of machines out there which is one stage. But there's a new tendency where you combine the pros from the screw press with the decanter, where you actually split the separation into two parts. And this means that you take most of the solids out with the screw press, and then you use the decanter technology for the fine polishing afterwards to achieve the same separation efficiency from the decanter. It removes some of the OPEX cost to the cheaper machines, and this is something we see a lot of where people are designing system for this. I have to take care of the time now. The biggest difference between manure and digestate is actually the know-how on separation efficiency. You saw in the beginning of my presentation that you have cows and pigs basically, and then small variations in between that. But it's fairly easy to create an overview on what you can do with separation efficiency depending on which feedstock you have. When you have a biogas plant, it's nearly impossible to predict this separation efficiency because the feedstock to the biogas plant changes all the time. Basically, they put whatever they can get their hands of into the biogas plant, which on the backside of the biogas plant creates different environments in terms of nutrient handle and so on. It creates, as soon as you introduce a different feedstock to the biogas plant, then you also tamper with the particle size distribution of the products you are handling, and then that will be influenced on the separation and so on. We have created internally in GEA a task force where we are looking at this and doing a lot of testing and so on and collecting data and so on. But it's a huge task, and it will create. I think we will work with that for maybe 10 years before we actually have a feasible document and an overview of what can be done with separation. The machines work and they will separate, but it's kind of shit in, shit out basically. So it will separate and so on, but it's actually the separation efficiency is completely dependent on the feedstock. And if the feedstock changes all the time, then it's very difficult to predict what the separation efficiency will be. Yeah, it's fertilizer. Today it's going for fertilizer. It's kind of the same thing as I did today. So the biogas plant, when they are going for separation, they have these two options. They go for, normally we actually see biogas plants that uses a double decanter setup. There's pros and cons between that, especially if the pro is that if you want to use polymers on before the second stage, then if you have the first stage where you remove most of the particles, then the polymer consumption is lower compared to when you set up a screw press versus a decanter like we have here. The first stage can be exchanged by a screw press, but we actually see that the people who need to use polymers in order to have the best possible separation efficiency, they go for a double decanter setup actually, which is more expensive on the service side. But if you actually need it, then this is the best overall performance you can get from a separation system. I put this picture in just to give you an idea on how the products looks like, and this is where we go. It could be digested as well. It's just in this case it's manure, and a typical pig manure that is separated into two steps, and there you between the between the first and second step, we have added a precipitant and actually also polymers, and we can actually get to a really fine where most of the particles are actually removed, which means the suspended solids are removed. It's just to give you an idea. So it's not enough. We see that. So separation with double decanters or even screw presses and decanters with or without polymers is not enough. The small amount of particles you see on the very right side of the screen, that small amount is actually too much if you want to do evaporation of the liquid. Basically, we have biogas plants which is completely based on food waste, and there basically you need to evaporate the water to the end, so you actually end up with a solid fraction of nutrients which can be handled then. So what we see now is actually that we have inquiries coming from what can we do more on the separation, and there we are looking into the third step. Our friends from Flodvik has a machine that is available to doing that, and we have a machine centrifuge available for polishing the centrate even further. So this is something we are working on and testing and looking into introducing to the market actually. Yeah. End of my presentation. I think there was a question.
Richard, thank you very much. Thank you. I was asking for a question, but thank you for your presentation from your 15 years experience point of view. I have a question actually. You said that you guys are not cheap, you are expensive. If I'm a farmer and I'm approaching you, and there is a question about 1 or 2 stages of your technology, 1 or 2 step stages. I mean, when it's time to speak about 2-stage setup for my business, let's say.
The large scale farmers in Denmark, the biggest farmers in Denmark for pigs are quite big actually. If we take that as an example, basically the machine for those guys will cost, when we're talking a system here basically, right? We come with a container with all the screw conveyors, pumps, all that is needed, electrical installation and so on. Then a machine for those guys will cost 300,000 euro. So it's quite expensive, and we have seen that service cost, because it's a very high, wear and tear on the machines are extremely high in this application actually. So we have seen service cost around €1 per cubic meter. So that's very large. That's very much actually on the service cost. So it's a very hard. So that's why we're also looking into this, or the industry is looking into this, utilizing the screw press, because the screw press is much cheaper to run with basically. So if you put all the wear and tear on the screw press, then you can use the decanter as a polishing step. And if you remove most of the sand with the screw press, then the wear and tear on the decanter is much lesser. But it's very, the first the first screw press decanter has been set up, I don't know, 3 years ago. And it's first now that we get the experience on the wear and tear of the machine. It will come much later, basically. But it seems like the wear and tear on the machine, when you have a screw press in front, are much lower compared to the 1-stage separation.
Thank you. Inga, do you have any question?
Well,
I'm asking.
No more questions.
No more
Thank
questions.
you for thorough presentation. Everything seems very clear.
Yeah,
Sounds
it's
good.
clear. Thank you very much, Richard. And now virtual applause again goes to you. Now let's transition to our next agenda item. Last, actually, our final topic of the day. And we have interactive feedback survey. And this will be led by Amalie Lunderwald. Amalie?
Yes. Can you hear me properly?
Yes, we can hear you.
Great. So in the chat, I put a code for the Mentimeter we will use. So if I may encourage everyone to access menti.com and use the code in the chat. And then I will share my screen to take you through the Mentimeter.
So we need to act right now, yeah?
Yes, and you can use both your smartphone and the browser, whatever suits you the best. Okay, so this part of the webinar is part of the BREC project, and as a part of the BREC project, we are also having these webinars, including this interactive feedback survey. And the reason we're doing it is because we are supplying these fact sheets, the easy read info material to distribute to different actors, and we would like some feedback on them. Okay, let's do this then. Okay, so I have all the answers. That's great. Next question. Building on today's webinar topics, what would you be interested in learning more about? Are you able to open Menti mode? Are you able to actually? Yeah, great. This is great.
So we can count responses online. So 10 responses already, yes. 12. Yes. Very nice.
Great. I'll give you one more minute to put in some words. 18 responses, that's great. Okay, I think we have some good responses here. I will move on to the next question. If there are 19 responses, 21, great. There is still coming something in. I think these are all very nice topics. Okay, I will move on to the next question then. Thank you very much for your responses. So this is our first, or this is like a draft for our fact sheets, or our the fact sheets that we will distribute. And I would like to get feedback on them. So I will just take you quickly through our first draft. It's circular phosphorus practices. And first, in this brochure is a page about how phosphorus is actually a vital resource for life, for plant growth, for everything we are very dependent on. So that's the first page. And the second page is how phosphorus actually follows a cycle, like a phosphorus cycle, and how it moves through soil, water, and living organisms, and playing this vital role that is explained also in the first page. So this is a picture that shows our phosphorus cycle. And then in the third page, we highlight some of the challenges, and we focused on its importance for food security, and also this that has been mentioned, how phosphorus is it's increasingly contaminated with cadmium as an example, and also that there is a geopolitical insecurity with phosphorus due to its locations of the reserves. And the second challenge is eutrophication, and how extensive use of phosphorus can give us bad conditions in our water reserves. And the last challenge we highlight is the inefficient use, and with the main focus on the linear use of phosphorus and not this circular use that we aim for. So these are the three main challenges that we focused on. And then in the last page, we talk about struvite extraction as a solution to how we can perform more circular use of phosphorus. So yeah, struvite is highlighted as an example, but we can also include more solutions to the phosphorus problem. So this is the brochure that we would like to have some feedback on. So in these bars, you can rank the statements from strongly agree to strongly disagree, to whether you find the information insightful, if it's easy to understand, and if you want more technical information, all these bars that you can pull towards whatever fits your opinion. And if you want, I can also go back to the brochure if you need to read more, but yeah. Oh, great, I already got a lot of responses. So I will give you a little bit of time on this one. I can see that we have 17 responses, 18. Okay, I think I will move on to the next question now, if everyone has answered. This is the last question, and you can rank these bars regarding the importance of the following type of information when comparing bio-based technologies. And you can rank them, you can just drag them up and down to what you think are the most important information when comparing these technologies. And let me know if there is anything unclear. I will try to explain. Great, I can see a lot of results coming in. "17 responses, 18. I think it's pretty clear that the environmental benefit of utilizing the technology is the main important, or the most important thing to address in these info brochures. So that was actually my last slide. If everyone has put in the response, that was one more. I think I will finish this then. Stop share. So thank you very much for all your responses.
Thank you, Emily. I think, I hope these answers will be useful organizing the next webinars. And actually, this is a brilliant way to finish our first part of this 3 days webinar. Thank you, Emily. And hereby, actually, we complete the first webinar, technologies paving the way to the circular bioeconomy. Once again, I would like to say many thanks to all today's presenters and all the listeners and participants. I hope they gain some new knowledge here, as well as I got some new knowledge. And if our last time, I would like to say many thanks to our organizers, Amalie, Inga, Selma. Thank you very much. And you know, let's try not virtual, real applause. Let's see how it works here. Yes, I can hear. At least. Thank you. I think it's good. We did a great job, and now I would like to invite you and warmly welcome to join us again next 2 Fridays, next upcoming Fridays, to the 2nd and 3rd webinar. Yeah, that's it. Inga, you want to say some words at the end?
No, just many thanks to everyone who devoted his or her time for today, and see you again next Friday.
Yeah. Until next time, take care and goodbye.
Thank you.
Thank you. Goodbye.
Bye.
Bye.
Goodbye.